Welcome back. So you saw that there are tables, there are trees, there are graphs, and there are cubes. So now we are looking at the last one of the structured or semi-structured shapes. The fifth one is text or images or video. Before we start on this, I will ask you a question that you might not know the answer, but this is part of what we are going to discover. But I just want to make you think a little bit. So I'm moving over to this. So by now, you are aware that when we have a different shape, the data is a specific shape, so we need to have the appropriate environment. We need a data model for the data. We need how to validate the data. We might need a query language. We need an implementation that is either a data lake or based on ETL, importing the data. And so it's the same for cubes, right? For cubes, we also have systems that specialize in cubes. We have syntax for cubes. We have query languages for cubes. We have data models for cubes. But there is something that we will see here and that we might not have really looked into before, is that even though the shapes are different and the systems are different, with the magic of data independence, it's possible to take a shape that the user sees, and hidden from the user, you actually store everything in a different system with another shape. And it turns out that you can do it with cubes, storing them as tables. You can take cubes, at least I'm pretending that you can. So you expose a system that deals with cubes. But internally, because again, you're lazy, you don't want to implement from scratch, you're actually going to use a relational database in secret, but it's all hidden from the user. So how do you think we can do that? How can a cube be stored physically, hidden from the user, in a relational database? First answer, a cube is always two-dimensional, so that's a table already. Second answer, with a star schema or a snowflake schema where dimensions metadata is outsourced to satellite tables. Third answer, by hitting it strongly with a hammer until it fits. And fourth answer, it can't. These are totally different data models, and the storage layer needs to natively support cubes. Okay, we have a majority. And the majority is correct. We will see that indeed you can use something called the star schema or the snowflake schema if you're really a big fan of data normalization and normal forms. So indeed, we can use a star schema or snowflake schema. I will show that to you, of course, in the slides that we are going to have. The answer about hitting it with a hammer is not completely wrong, actually, because people actually do that in reality. But you have to be careful when you do that, because if you want to take data in a certain shape, trees, tables, cubes, and so on, and you want to force fit it into a system that normally is made for other shapes, you're going to be in for a big surprise in terms of productivity and performance. You might end up with something that is super slow or very difficult to write the queries and so on. So you have to be aware of that. You can, that's the scary thing about it. You can always do that. You can always force fit data that doesn't have the right shape into a system that is a different shape. It will always succeed. But again, it's going to be slow and not productive. So you have to think about it. How do you do it? If you think smartly about it, in some cases, you will manage to store it in a way that, at least from a performance perspective, is going to work. But since from a productivity perspective, the experience will not be awesome, you still need to provide it as the physical storage and provide a logical layer. And then the user will have a language in the proper shape. All right, I will also say more about that next week in the wrap-up, right? But generally, you can force feed trees into relational databases, actually very tough, but you can. You can force feed tables into collections of trees. That is surprisingly easy, actually, because we saw that tables are flat collections of homogeneous collection of trees. You can force feed graph databases into relational tables, right? With the triple store, you can just create a relational table with 3 columns, 1 triple per row, and that works, right? So you can really, it fits together, right? You can store, use a different shape as the physical layer. All right, but now I'm closing the parenthesis. I also want to say the fourth answer, MOLAP, actually exists. What's wrong about the fourth answer is only that it's not true that it can't, right? So there is the relational approach called OLAP, and there is also MOLAP. So it's because of the it can't that the answer is actually false. All right. And the first, so a cube actually can have many, many dimensions and not just two. So let me return now to the slides. It's opening. Okay, and we are back. All right, and my hope is to finish today with what I want to tell you. So first, a bit of history. How did data cubes appear into the whole ecosystem? Well, you know that in the 70s, that's the age of transactions. This is where the relational database systems were invented. PostgreSQL, IBM, Microsoft SQL Server, Oracle, and so on. So it's now 53 years old. Dates back to 1970. In the 1990s, people started noticing that you can do business stuff with data. You can actually create fancy pie charts for the C-level people, and that's called the age of business intelligence. In fact, this is how data cubes were born as part of these periods, right? And then we have the age of big data. That is what we covered a lot in the lecture. That was actually later in the 2000s. That's with parallel distributing processing, heterogeneous data set, messy data sets, denormalization, trees, graphs, and so on. All right. But the interesting thing is that cubes are actually older. Cubes really date back to the 1990s. All right. So now I'm going to throw some acronyms at you. But in fact, I'm going to be throwing them at you knowing that you already actually know what that is. You just might not have known it was called that way. In some cases, the queries that you need to run against your system involve a lot of updates. That's the case when you have a website like a web shop, people place orders, they create customer profiles and so on and so on. You're going to have a lot of updates, thousands of updates every second. If you're a big website, maybe even more. This is called OLTP, online transaction processing. It's just a name for really, these technologies, the relational databases, PostgreSQL, MySQL, and so on. These are all OLTP technologies. This is the beautiful world of the normal forms where we want to avoid trouble with data duplication. So we just normalize the data into plenty of tables and we let the queries, the updating queries run against it. We can still also have select from where, right? But there's also a lot of updates. On the other hand, we have OLAP, online analytical processing. This is when we read the data. We never modify it, we just read it. But think about it, we've been doing that the whole semester for weeks. What did we do with MapReduce, with Spark? We just read the data. You drop the data on a data lake and then you read the data, right? So in fact, we've been doing OLAP the whole semester. I just didn't call it that way. So this is read intensive. This is write intensive. Now, why did I put a table above OLTP and a cube above OLAP? It's not that it has to be this way, because you can have OLTP with any shape and you can have OLAP with any shape. We've done OLAP with trees the whole semester. It's just that historically, the first thing that people imagine in their brains when they think OLTP, they will think of a relational table, because very often people use relational database systems. And when you say OLAP, people will very often think of a cube, but again, this is because it started with cubes in the 1990s. So this is the reason why OLAP still makes you think of cubes. But again, today you should be aware that this is not tied to the shapes as it was in the past. The both can apply really to both cases. So for example, with trees, you can have OLTP with MongoDB. MongoDB actually can do OLTP on trees. And OLAP would be with Apache Spark, data frames and so on, data frame APIs. That would be basically OLAP. For whom is that clear? Right, so that's OLTP and OLAP. And again, the idea here is that for OLTP, you're running your business in the day-to-day job. And for OLAP, it's more like you throw something in the data lake, you don't touch it anymore. It's like taking a photography and not touching it again. And you just run analysis on top. That's really for decision support. It's to create the fancy charts that the CEO will see, and then they make the decisions for the company based on that, right? That I've already told you. OLTP, lots of writes, OLAP, lots of reads. OLTP, the fact that you write a lot means that a lot of the queries on OLTP will touch very little data, right? You do a search on TVs, for example, and then it's returned on the website. It's only going to touch the 10 products that you ask for. When you create customer information or change your address, you're only touching your specific information. It's very fine-grained, detailed records, like very little data at the same time. That's the reason it's fast, because we have indices, remember? Hash indices, B+3s, and so on. So this is why it's very fast. OLAP, on the other hand, keeps aggregating everything. We just scan the whole data, we aggregate, it's consolidated, summarized, and so on. And that's just an example of the sort of things you can get out of the system. But all of these fancy charts here typically come from the aggregation of massive amounts of data. So that's one more contrast that you can establish between the two. And finally, and that shouldn't surprise you, in the world of OLTP, where we keep the data in high normal form in multiple tables, we're going to have to sometimes join the tables, right? But again, we look at small portions of the data. In OLAP, however, since we aggregate and look at large scales, technically, we look at the join of the whole data. In fact, we have so many joins and so many heavy queries that we want to denormalize the data in order to avoid the joins. And you remember that denormalizing the data means joining the data, right? It's the same, and denormalizing is normalizing is the opposite of join. Who remembers that? Right? Okay. Okay, so that's the idea, and for this reason, OLTP is very fast. It's really a matter of milliseconds. OLAP, I told you for MapReduce, can take hours. You can come on the following day in order to see the results, right? Some systems will work in maybe 1 or 2 minutes. So then you can sit in front of your spreadsheet software and wait for the results, maybe go for a coffee, but it can really take hours and more here. So OLAP is really slower. And finally, and again, I'm just repeating myself, but that's the goal. Since you know that in OLTP, we are in normal form, the data is consistent. There are not too many duplicates because we have these normal forms and it's over multiple tables. But in OLAP, since we read a lot and we don't need to update the data, we don't care about consistency. We just care about redundancy, redundancy, redundancy. We denormalize like crazy. We build a gigantic, nested, heterogeneous data set out of this. And it's all redundant. But again, since we just read the data, we don't care that it's redundant. All right. And finally, I will leave that for you offline. If you want even more ways to contrast OLTP and OLAP, then this is an even longer list, right? My goal is to give you an intuition that these are really two different worlds, and there are systems designed for OLTP and there are systems designed for OLAP, for all shapes. So now I'm going to dive deeper into this, having in mind more of the cubes, but again, for historical reasons, because this all started with cubes. So the idea, there's 4 adjectives to characterize OLAP. 4. The first one is that it's subject-oriented. It's just a fancy way of saying that usually when you run business analytics on OLAP, you have a very specific goal in mind. For example, you're looking at your sales data of your company, or you're looking at your customers, or you're looking at scientific data for CERN, for example, or you're looking at census data in the US. It's one of the oldest use cases for computers, the US census every 10 years, and so on and so on and so on, right? So web analytics is yet another one. So we say that it's subject-oriented because usually the cubes you build are really with a very, very specific goal in mind for the data you're targeting. The second adjective is that it's time variant. Again, sounds very fancy, but all it really means is that you want to go back to the past when you do that kind of analytics. For example, you want to look at your sales number over the past 10 years, 5 or 10 years, typically. In OLTP, we don't really care about the past. You just have the business running on a day-to-day basis. You just want to know right now what are the orders in the system, what are your customers, and so on. You don't care so much about the past. The past really matters when you want to aggregate data over large scales and look and analyze your business, right? So this is why it's time variant, because the time is very, very important. And typically, you go back 5 to 10 years. It's really for practical reasons that we don't really go back much more than that. It's just that if you go back more than 10 years, things have changed so much technologically that it becomes very expensive. We had a continuing education student who was who explained a bit his experience with this in his company a while ago, shared with the class. And he explained that they even found data of a century ago that was even on paper. Like they had to manage the water pipes and of the building and so on. That was not even in computers. So just to tell you that pragmatically, we just go back 5 or 10 years, which usually can be done with reasonable costs, right? And so the idea is that when you want to do business analytics, you basically need to take a photography, a snapshot of your system at that moment, including maybe the past 10 years, and then you freeze it. You drop it on some data lake or whatever, and you don't touch it anymore. It's there, no updates anymore. It's frozen. Then you just analyze it, but without touching it. So this is the snapshot. So you load it. It sounds trivial, but costs a lot of money. But you take the snapshot, store it, that's it. Then you just query it, no updates. Now, how does that work? How do you actually take that snapshot? It's actually very complicated, and that's a real-world problem. So imagine you're tasked to do that. You work in a company, and the company asks you to take a snapshot of all the data for the purpose of creating reports for the high management. And they think, okay, I'm just going to log into the PostgreSQL database, and I'm just going to have some select start from where query from all the tables, and that's it, right? Then you start doing it. I don't give you 1 hour until you get people knocking on your door complaining about what you're doing. Because you're trying to export the entire database, slowing it down, slows down the whole business, disturbs everybody in the company. That's the first real-world trouble that you have if you try to do that. For this reason, it's done in the night. When nobody's here in the office, you just schedule the exports in the night and automate it and so on. And then when nobody's using the system, this is when you can take the snapshots and move them over to your to the OLAP system. By the way, the name for that system, the OLAP side, is called a data warehouse. This is the fancy name that we give to where it takes the snapshot and put all of that data, the data warehouse. So a relational database is one of the places where you want to take the snapshots, but you probably have plenty of other places where you want to do that, maybe some files, customer relationship management system, ERP systems, and so on, right? So during the night, you take the snapshots, then you put them into the data warehouse, and then the fun begins, and you can analyze, build reports, maybe use even machine learning in order to get insights and so on, right? So this is the idea. You take a snapshot, and then you work on that snapshot. And technically, when you do that snapshot, you have to do something that I've already told you about. It's ETL, extract, transform, load, because you cannot just take the snapshot and drop it, right? You need to actually feed it into the data warehouse in a usable way, and that can cost millions of dollars. In fact, typically in these projects, this is when you get the fancy consulting companies that come into play and help you doing that. You basically need to, sometimes update the snapshot every couple of weeks or months. You need to build gateways between the systems. You need to clean up because usually the data can be very messy, except, for example, when it comes from logs. You have some transformations like this. You might have, especially in Switzerland, right? Some might be in French, in German, and so on, like the titles and so on. And then you have to load it into the system, which again, you need to create the schemas and so on. So yeah, there's plenty of IT consultants who actually have a full-time job doing that sort of things. All I want to say is it's very complex, costs a lot of money. So extract, transform, load, right? Since it's such an important thing to do, what happened is that in the 90s, a few small companies were created, S-Base, Cognos, and so on. And then they were purchased by the giants who noticed that there is a synergy between relational databases and business analytics. So this is how it has consolidated. Now you have Oracle, IBM, Microsoft. That shouldn't surprise you. These are the big three, plus SAP. So there's actually these 4 big players, right? And so S-Base is the name of the OLAP/data cubes in Oracle, Cognos for IBM, analysis services for Microsoft, all right? Okay, so this is for the historical perspective and the context in which we do this, right? So we have the day-to-day business, we need to take some snapshots to run our analytics, preferably during the night. And once we've dropped everything in the data warehouse, then you can start querying the data. Now, what I'm going to do is look into the shape of data cubes from a logical perspective, very high level perspective. So what does the data model look like? In fact, we've already done that for graphs, we've already done that for trees, and you've already done that for tables in the relational database management lectures in your bachelor's. All right, so let's look at the data model for cubes. So what is a cube? Well, I built a three-dimensional cube just so that, because 3 dimensions is kind of what we usually visualize in our minds. So imagine that we look at several years, we look at several products that the company is selling, and we look at several countries. What's going to happen is that if I take a specific year, a specific product, and a specific country, that gives me the coordinates of a specific little cube right there. And in that cube, there is a value 7 in that example. And imagine that the year of that layer is 2022. The product here is the servers, and the country here is Switzerland. Maybe this is Austria and Germany, right? So 7 servers sold in Switzerland in 2022. And we have the same in every other little cubes in there for every year, every product, and every country, right? Cubes can have more than 3 dimensions. They can have 4, they can have 5. 4, who manages to visualize 4-dimensional hypercubes? Some of you, right? This can still kind of be done. 5, that's almost impossible for any human being, right? So this is why I didn't bother you with more. But in OLAP, you can have 5, 6, 7, 10, 20 dimensions. So you can have a lot of that. But if you've looked at linear algebra, I'm sure you're not scared of dimensions, right? You even have vector spaces with infinite numbers of dimensions. And we can think of in an abstract way about that. It can also be 2 dimensions or 1 dimension, of course, but usually it's rather more dimensions. Now, what kind of dimensions do we have? Well, typically we have time, as I told you. So the years, the quarters, the months, the dates, the days, and so on. We might have where. It might be by geographical locations, by countries, cities, and so on. Can be what? The kind of products you're selling. Can be the currency. Maybe you want to separate between dollars, euros, Swiss francs, rupees, yuan, and so on. And many, many more, right? Who, if you have salespersons, then you want to also look at the data for the teams, for example. So these are the kind of dimensions you can have. Some people say axis for a dimension, but it's really just a matter of terminology. Now, here's the problem. If you look at the cubes like this, and it has a high number of dimensions, you just cannot possibly imagine that in your head. So what we do, there is a trick that we actually use. We take that cube, we hit it with a hammer, get all the little cubes just all over the place, and then we pile the little cubes up on top of each other. 1 little cube, 1 little cube, 1 little cube, 1 little cube. And we get that. We basically have, for every little cube that we get, we have 1 record. And in that record, we put the values of the dimensions. So Germany 2022 Peter, for example, that's one of the little cube, maybe, I don't know, this one. We put it there together with the value. Then this is another little cube with the 3-dimension values, and then the value it has. Then another little cube, another little cube, another little cube. This here is what happens if we take a 2 by 2 by 2 cube, right? There's 2 values for the countries, 2 values for the time, 22, 21, and 2 values for the salespeople, Peter and Mary. So it's a 2 by 2 by 2 cube. So that would be, imagine that portion here, 2 by 2 by 2. If I hit it with a hammer and pile up the 8 little cubes like this is what I get. This is called a fact table. The beauty of a fact table is that it fits in a relational table like this, so it only takes 2 dimensions, and that we can actually take a look at as a human and understand. You just need to remember that even though it looks like a table, it's really just a view over a cube, right? And you see the dimensions of the cubes in these attributes, and then the little values in each little cube in there. For whom is that clear? Right? Awesome. So this is called a fact table. It's a view in the form of a relational table of a cube. And now you see we can have as many dimensions as we want, right? We just get more columns, more attributes. Okay, now you might also see this, especially if you work in business reporting. This is just in order to help a bit people understand what's going on. So it's common to add this square bracket member to say that this is a member of a dimension, square bracket axis to basically say this is a dimension, so that actually you might see. So I'm going to do this during the course just to clarify what is a dimension, what is a value of a dimension. So you see axis and member. All right. All right. So now we have our models. We have the data cubes. We associate some specific coordinates in a cube with one value that we put in the little cube. And we can represent the cubes in this flat view called the facts table, one little cube per record. The order doesn't matter in here of the little cubes. They just need to be there, but we don't care in which order they are listed, of course. So now that we have the data model, we are going to use it and do things with it. So what can we do? Well, for tables, we can select, we can project, we can aggregate, we can order, we can join. What do we do with cubes? Well, the first thing we can do is slice. We slice a cube, and that means what you see on the visual, you just take one value of a dimension and take the layer and take it out of the cube. So here I did it horizontally, but you can do it in for any dimension. This is called slicing. And the idea is that if you take this cube, well, technically the fact table of the cube, and slice it on Switzerland, you get this. Right here, you have Switzerland and Germany. If I take the slice corresponding to Switzerland, I get this. Bonus question, if I want to use the relational model, and I look at this as a relational table and this as a relational table, what relational algebra operator do I need to get that? A filter, yes, also called a where clause, yes, absolutely. And the relational algebra? Yes, a selection, exactly. So this is a selection. So what we've just seen is you can implement slicing. So slicing is on a cube, but on the underlying representation as a fact table, this is in fact a selection. But the selection now is a physical implementation, while the slicing is the logical operation that you do on the cube. Very good. So then what we do, what we like to do, because again, it's fancy reports, very shiny. So instead of repeating Switzerland all over the place, we move it up like this. We'll do the same with dollars because it's dollars everywhere. And so we'll put it's called slicers, we'll put them here. So this basically applies to everything. So the location is Switzerland everywhere, US dollars everywhere. Now we have the period, the salesperson, and the values, and these two additional dimensions sliced. Who is following? Okay. Now we want to be even fancier than that, because that still look a bit like technical, right? What if I would rearrange these four little values, because now I only have two dimensions left, right? If you don't consider the ones we sliced, I have two dimensions left, period and salesperson. But I know how to display a cube in 2 dimensions on a sheet of paper, right? It's easy, like this. So we can do it. So we basically put one axis, so the salespersons on the rows and the time on the columns. And we said that we diced the dimensions. We dice on the row and we dice on the column. And now I have a 2-dimensional cube, but that's because I sliced. And you might have heard slice and dice. You slice and dice data cubes. This is actually almost a buzzword that you even see on social media. This is slicing and dicing. In fact, a few years ago, I even came dressed as a cook. I went to the bakery in the morning and asked, oh, do you have a piece of bread shaped like a cube? They did have one. So I came all the way to the lecture with my bread shaped like a cube, and I sliced and diced in front of the class to basically show how it was done. But I'm sure you have the visuals of this. This is basically how it works. All right. And if you want to be even fancier, then these are the kinds of views you see also in business reporting with these shades of typically blue that is used. Here I use purple, but typically shades of blue like dark blue, light blue, and so on. All right. So this is what you get in the system. All right. And typically, in order to create this view, this is called a cross-tabulated view. That's the fancy name of what you see on the screen. It's called cross-tabulated view. You basically look at your cube, which might have 10 dimensions, and what you need to do is select 2 of them, typically, that are the dicers. You put them on the rows and the columns, and everything else you just slice on, right? You take a slice for the other dimensions. I'm saying 2. It could be 1. 1 also fits, right? You just, for example, don't use the rows or don't use the columns. 3 is a bit challenging because you don't have 3 dimensions in a screen. If you really want the 3rd dimension to dice on, you typically make them sheets, just like in a spreadsheet. So you have little tabs at the bottom and you can click on them. That would be the user experience. But again, typically it's 2. You basically dice on 2 dimensions and slice on everything else. Yes?
I'm trying to see what's special about this. Like, we've just created a primary key, a composite primary key with kind of n options for each one, and now we've shoved it into a database. What's so good about that?
You'll see right after the break, because in fact, there's many other things we can do with the data. It's a whole different universe, basically, to query the data. But we'll get to it right after the break. I will show you all that, right? Okay, see you in 15 minutes.